Let's break down tricellular meridional circulation even more simply, step by step. Step 1. What is the tricellular circulation? The tricellular circulation is the way air moves up and down in three big loops between the equator, the middle of the Earth, and the poles, the top and bottom of the Earth. These loops are like a giant conveyor belt, carrying air, heat, and energy around the planet. These three loops or cells are Hadley cell, close to the equator, Ferrel cell in the middle, polar cell near the poles. Hammer 2. Why does air move? Air moves because the Earth gets uneven amounts of heat from the sun. The equator gets more heat because the sun shines directly on it, while the poles get less heat because the sun's rays hit them at an angle. To balance out the heat, air moves. Warm air rises from the equator and cold air sinks near the poles. This creates the three big loops. 3. The three cells, loops. A. Hadley cell, close to the equator. Warm air rises from the equator because the equator gets a lot of heat from the sun. As this warm air goes up, it starts moving toward the north and south. When the air cools down around 30 degrees north or south, it sinks back down to the Earth's surface. The sinking air moves back to the equator near the ground. Example, think of a hot air balloon. When you heat the air inside the balloon, it rises. When it cools down, the balloon falls back. The Hadley cell works like this. Warm air rises, moves away, cools down, and then sinks. B. Ferrel cell, middle loop. The Ferrel cell is between the Hadley cell and the polar cell. Air from the Hadley cell, which sinks at 30 degrees latitude, moves towards 60 degrees latitude. Here, the air warms up and rises again. Example, imagine two gears. When one turns, it makes the other gear turn in the opposite direction. The Ferrel cell connects the movement of air between the Hadley and polar cells, just like connected gears. C. Polar cell, near the poles. At the poles, the air is very cold, so it sinks. This cold sinking air moves toward the equator near the surface. Around 60 degrees latitude, the air gets warmer and rises again. Example, think of cold air as being heavy. When cold air reaches the ground near the poles, it sinks. As it moves closer to the equator, the air warms up and warm air rises. How does this help the Earth? This whole system of three cells, Hadley, Ferrel, and polar, helps to spread the heat from the equator to the poles. Without these air movements, some places on Earth would be too hot near the equator, and others would be too cold near the poles. And 5. Other factors. Angular momentum and kinetic energy. When air moves, it also has kinetic energy, energy from motion, and angular momentum, energy from spinning with the Earth. Kinetic energy. When air moves, like when you walk or run, it has energy. This energy is called kinetic energy. B. Angular momentum. The Earth spins on its axis, and air moves with it. Air near the equator has to travel a longer distance around the Earth because the Earth is wider at the middle. So, air at the equator moves faster than air near the poles. 6. Summary. The tricellular circulation system has three loops that move air around the Earth. The Hadley cell, Ferrel cell, and polar cell. Hadley cell, air rises at the equator, moves toward the poles, and sinks around 30 degrees latitude. Ferrel cell, air rises around 60 degrees latitude and connects the Hadley and polar cells. Polar cell, air sinks at the poles and moves toward the equator. This system balances heat and energy, making the planet more comfortable for life. Let's break this down into simpler terms and explain it clearly. 1. What is poleward momentum transport? First, let's understand momentum. Momentum is the energy something has because it's moving. For example, a fast-moving car has a lot of momentum. Now, poleward means toward the poles, the North Pole and South Pole. So, poleward momentum transport means moving energy, or momentum, from the middle of the Earth, around the equator, to the poles. 2. Westerlies and easterlies. Types of winds. Westerlies. These are winds that blow from the west to the east. They are found in the temperate zone, between 30 degrees and 60 degrees latitude, both north and south. Easterlies. These winds blow from the east to the west. They are found near the equator in the tropical region. 3. How momentum moves with winds. A. Westerlies in the temperate zone. In the temperate zone, around 30 degrees to 60 degrees latitude, the westerly winds move fast and give some of their energy, momentum, to the earth through friction. Friction is like when you rub your hands together, creating heat. When the wind rubs against the earth, some of its energy is passed to the surface. B. Easterlies in the tropics. In the tropical region, closer to the equator, the easterly winds are moving from east to west, but they are gaining energy, also through friction with the earth. This energy doesn't stay in the tropical region. It gets moved or transported toward the poles. And number 4. The role of the subtropical jet stream. The subtropical jet stream is a very fast-moving wind current high up in the atmosphere, around 10 to 12 kilometers above the Earth. It is located near 30 degrees latitude, both north and south of the equator. Barry and Corley, scientists, say that the most momentum or energy moves toward the poles around this area where the subtropical jet stream is. This happens at a very high level in the atmosphere, around 250 millibaud. The term 250 millibaud means the height in the atmosphere where the air pressure is 250 millibars, which is quite high up. Summary: winds, like westerlies and easterlies, help move energy, momentum, around the Earth. Westerlies give some of their momentum to the Earth through friction, while easterlies gain momentum from friction in the tropical region. The jet streams, especially the subtropical jet stream at around 30 degrees latitude, play a big role in moving this extra energy toward the poles. Let's break down the information about the tropical cell's upper air circulation, focusing on the anti-trade winds and subtropical jet stream. Upper air circulation in the tropical cell. 1. Anti-trade winds. What are they? Anti-trades are high-altitude winds that move poleward from the tropics. They are found above the trade winds and travel from the equator towards higher latitudes. Current understanding: irregularity. These winds are not always steady or continuous. Their movement can vary widely depending on the longitude, east to west position, and season. Continuity: eastern oceans. In the eastern parts of the oceans, especially in the southern hemisphere and during colder seasons, the anti-trades tend to be more consistent. Continental land masses. Over land, especially in the northern hemisphere, the anti-trades are more irregular and often interrupted. 2. Subtropical jet stream. What is it? The subtropical jet stream is a high-speed band of westerly winds moving from west to east, found at about 12,000 meters above the Earth's surface. Seasonal variations. Northern hemisphere. This jet stream is mainly present during the winter months. It is stronger and more prominent then. Southern hemisphere. In the southern hemisphere, the subtropical jet stream persists throughout the year, especially around 25 to 30 degrees south latitude. Number 3. Tropical easterly jet. What is it? This is a high-altitude jet stream found around 10 degrees north latitude. Seasonal presence. During the summer months in the northern hemisphere, the tropical easterly jet replaces the subtropical jet stream over Asia and Africa. Summary: anti-trades. Move from the tropics towards higher latitudes. Not always continuous. More stable over eastern oceans and during colder months in the southern hemisphere. More interrupted over land areas. Subtropical jet stream. High-speed westerly winds at about 12,000 meters. Present in winter in the northern hemisphere and year-round in the southern hemisphere. Tropical easterly jet replaces the subtropical jet stream in summer over Asia and Africa. In essence, the tropical cell's upper air circulation is more complex than previously thought, with significant variations in wind patterns depending on location and season. Let's break down the details of the tropical cell circulation, focusing on the subtropical jet stream, the tropical deserts, and the trade winds. Key features of the tropical cell circulation. 1. Subtropical jet stream. Height, found around 12,000 meters above the Earth's surface. Characteristics. It is a fast-moving band of westerly winds from west to east. Northern Hemisphere. This jet stream is mainly present during the winter months. Southern Hemisphere. The jet stream persists throughout the year, especially between 25 degrees and 30 degrees south latitude. 2. Tropical easterly jet. What is it? A jet stream that appears around 10 degrees north latitude. When it appears, replaces the subtropical jet stream in the northern hemisphere during the summer months over continents like Asia and Africa. 3. Horse latitudes. Location. Near the center of the subtropical high-pressure zone where air descends. Characteristics. Light and variable winds. Significance. These areas are associated with many of the world's tropical deserts. 4. Trade winds. Direction. Northern Hemisphere. Northeasterly trades. Southern Hemisphere. Southeasterly trades. Function. Move from the subtropical high-pressure areas towards the equator. 5. Intertropical Convergence Zone, ITCZ. Location. Where the trade winds from both hemispheres converge. Characteristics. This region is known as the doldrums, characterized by light and variable winds. Theories explaining tropical cell circulation. 1. Thermal theories. Driving force. The temperature difference between the tropics, warm, and higher latitudes, cooler. Function. This temperature difference drives the rising and sinking of air, creating the Hadley cell circulation. 2. Dynamic theories. Driving force. Instability and self-reinforcing nature of wind movements. Function. Changes in wind patterns and air masses help maintain the circulation. Summary. Subtropical jet stream. High-speed westerly winds at 12,000 meters, present in winter in the northern hemisphere and year-round in the southern hemisphere. Tropical easterly jet replaces the subtropical jet stream in summer in the northern hemisphere. Horse latitudes, dry areas with light winds where air descends, leading to tropical deserts. Trade winds flow from subtropical high-pressure areas towards the equator. ITC doldrums, where trade winds converge at the equator. Both thermal and dynamic theories explain the tropical cell circulation, with thermal theories focusing on temperature differences and dynamic theories on wind patterns and instabilities. Jet stream. Explained in simple terms. Let's break down what jet streams are and how they work, step by step. 1. What is a jet stream? A jet stream is a fast-moving wind high up in the sky, in the upper troposphere, about 10 to 15 kilometers above the Earth's surface. These winds flow in narrow belts and move really fast, like highways in the sky where the air speeds up. The winds in jet streams blow from west to east. Example. Imagine a river of air high up in the sky, flowing quickly in one direction. That's the jet stream. 2. How fast does a jet stream move? Jet streams can reach speeds of over 200 miles per hour, 300 kilometers per hour. That's faster than most cars and planes can go. They don't always move in a straight line. They meander or wiggle across the sky, a bit like a snake. 3. Why do jet streams happen? Jet streams form because of temperature differences between the equator, where it's warm, and the poles, where it's cold. Warm air rises and moves toward the poles, while cold air sinks and moves toward the equator. This creates strong winds in between these two air masses. Example. Think of a room with a heater on one side and an air conditioner on the other side. The hot and cold air meet in the middle and create a rush of wind. Geostrophic winds. Jet streams are geostrophic winds, which means they are balanced by two forces. The pressure gradient force, which pushes air from high pressure to low pressure. The Coriolis force, which makes winds curve because the Earth is rotating. Because of this balance, the winds in jet streams can move at such high speeds. 5. Where do jet streams form? There are usually two main jet streams in each hemisphere. 1. Polar jet stream. This forms between cold polar air and warmer air from mid-latitudes. It is stronger, especially in the winter. 2. Subtropical jet stream. This forms closer to the equator and is less strong than the polar jet stream. Example. Imagine two racetracks, one near the Arctic Circle, the polar jet, and one near the tropics, the subtropical jet. The cars, winds, on the Arctic track go faster because there's a bigger difference in temperature. Hatch 6. How did we discover jet streams? Jet streams were officially discovered during World War II. When American bomber pilots flew toward Japan, they found that strong headwinds, winds blowing against them, slowed them down a lot. On their way back, they had tailwinds, winds pushing from behind that doubled their speed. These experiences helped scientists realize there were super fast winds in the upper atmosphere. How example, imagine you're riding a bike into a strong wind. It's hard to move forward, but if the wind is at your back, it pushes you along and you go much faster. That's what the pilots experienced. 7. Clues from the past. Even before World War II, there were hints that jet streams existed. In 1904, scientists noticed high-speed clouds in the sky, moving much faster than normal clouds. In the 1920s and 1930s, scientists launched balloons into the atmosphere and observed that winds were blowing much faster at higher altitudes. 8. Why are jet streams important? Jet streams affect the weather. They can guide storms and determine where weather systems go. They help move air and thus heat from one part of the planet to another. They also help planes. Airplanes can fly faster when they catch a ride in the jet stream, especially when flying from west to east. But flying against the jet stream can slow planes down. 9. How do jet streams affect weather? Jet streams create troughs, dips, and ridges, peaks, in the atmosphere. Troughs often bring cold weather and storms. Ridges bring warm weather and calm conditions. Example, think of a roller coaster. When you're in a dip, you're in a colder, stormy part of the jet stream. But when you're on a peak, you're in a warmer, calmer part. Recap. Jet streams are fast-moving winds in the upper atmosphere, blowing from west to east. They form due to temperature differences between the equator and the poles. They were discovered during World War II when pilots noticed strong winds during flights. Jet streams affect weather and help move air and heat around the planet. That's the simplified explanations. Would you like to know more details or explore another topic? Let's dive deeper into jet streams in a simple way, step by step. 1. What exactly is a jet stream? A jet stream is a very fast wind that blows high up in the sky, about 9,000 to 12,000 meters above the ground. Think of it like a river of air, flowing super fast, but instead of on the ground, it's far above in the sky. These winds blow from west to east around the Earth and are much faster than normal winds. Example. Imagine you're standing next to a calm river, normal wind, and then suddenly you see a speedboat zooming by, jet stream. The jet stream is like that speedboat in the sky, moving really fast compared to the regular air. 2. How fast are jet streams? Jet streams are incredibly fast, with speeds that can go up to 200 miles per hour, 320 kilometers per hour. They are much faster than the air around them. The speed of the jet stream can change based on seasons. In winter, they are stronger and faster because of the big temperature difference between cold and warm air. In summer, they are slower because the temperature difference isn't as big. Example, think of it like this. In winter, it's like you're skiing downhill, so you go really fast. In summer, you're walking on a flat road, so you move slower. 3. Where are jet streams found? Jet streams are located in the upper atmosphere, the troposphere, far above where we live. They are mostly found in the middle latitudes, which means between 30 degrees and 6 degrees north or south of the equator. They circle the Earth, going from west to east. Example. Imagine wearing a belt around your waist, but instead of just being still, it keeps spinning around you. That's like a jet stream circling the Earth. 4. Why do jet streams form? Jet streams form because of temperature differences between the equator and the poles. At the equator, the air is warm. At the poles, the air is cold. The big difference in temperature between the warm air and cold air makes the wind blow really fast in the jet stream. Example: if you open a window on one side of a house, warm air, and a door on the other side, cold air, the air will rush through quickly. That's kind of what happens in a jet stream. 5. What shape do jet streams take? Jet streams don't move in a straight line. They wiggle and bend, forming a wavy pattern as they circle the Earth. This wavy path is because of mountains, continents, and weather systems like cyclones and anticyclones, big areas of high and low pressure. Example: imagine a ribbon that flutters in the wind. It doesn't stay straight, but twists and turns. That's what jet streams do as they move around the planet. Number 6. Why do jet streams matter? Weather. Jet streams are super important for controlling the weather. They help move storms and other weather patterns across the planet. They can make certain areas colder or warmer, depending on how they flow. Airplanes. Jet streams can also help airplanes fly faster if they catch the wind moving in the right direction. But if a plane flies against the jet stream, it will slow down. Example: if you're riding a bicycle and a strong wind is blowing behind you, it will push you faster. But if you're riding against the wind, it's much harder and you'll slow down. 7. How do jet streams change with seasons? In winter, jet streams move closer to the equator and their speed increases. This is because the temperature difference between the poles and the equator is much bigger in winter. In summer, jet streams shift closer to the poles and slow down because the temperature difference isn't as large. Example: think of it like a giant fan that gets turned up in winter, faster winds, and turned down in summer, slower winds. 8. Jet stream and air pressure. Jet streams are caused by a difference in air pressure. At high altitudes, the air pressure gets lower, and the difference between the high pressure and low pressure creates the jet stream. The winds in a jet stream are mostly westerly, meaning they move from west to east. Example: imagine a balloon. When you let go of it, the air rushes out quickly, creating wind. The jet stream is like that rush of air, but in the atmosphere. 9. Why did we learn about jet streams during World War II? During World War II, American bomber pilots flying over Japan noticed that their planes were either moving much faster or much slower, depending on the wind they encountered at high altitudes. When they flew against the jet stream, their speed decreased. When they flew with the jet stream, their speed increased. This is how pilots and scientists learned about jet streams, and soon they became an important part of understanding weather patterns and aviation. Recap of the jet stream. 1. Fast-moving winds, high up in the sky, moving from west to east. 2. Caused by temperature differences between the equator and the poles. 3. Wavy and irregular in shape due to weather and geography. 4. Important for controlling weather and helping airplanes travel faster or slower. 5. Jet streams are stronger in winter and slower in summer. Now you know all about jet streams. They're like highways of fast air in the sky, helping to move weather and even affecting airplanes. All right, let's break it down step by step in simple terms. What is the jet stream? Imagine the atmosphere like a huge blanket of air surrounding the Earth. In this blanket, there are very fast winds high up in the sky, known as the jet stream. These winds flow like rivers in the sky, traveling super fast but way above where airplanes fly. Types of jet streams. There are 2 main types of these fast winds. 1. Polar front jet, found closer to the north and south poles. This jet stream is related to a boundary called the polar front, which separates cold air from the poles and warmer air from the equator. These winds can be super fast, sometimes reaching up to 480 kilometers per hour, as fast as some airplanes. 2. Subtropical jet, found closer to the middle of the Earth, near the equator, but much higher up in the sky, around 12 kilometers above the ground. This one is not directly related to any boundary like the polar front. Speed of the jet stream. The average speed of jet stream winds is around 144 kilometers per hour, like the speed of a fast car. During the cold season, winter, winds can go even faster, reaching speeds of 160 to 240 kilometers per hour. Inside the core, or center of the jet stream, winds can sometimes blow even faster, up to 480 kilometers per hour. That's more than 3 times the speed of a fast car. Seasonal changes and differences. In the cold season, the winds tend to be stronger because the temperature difference between the cold polar air and the warmer air from the equator is bigger. On the right side of the jet stream core, the winds are usually stronger than on the left side, but this flips when you're closer to the equator. Breaking through the tropopause. There is a boundary called the tropopause, which separates the lower part of the atmosphere, where weather happens, from the stratosphere, which is higher up and normally dry with no clouds. Sometimes, the jet stream winds are so strong that they can break through the tropopause and go into the lower part of the stratosphere. The stratosphere usually has no clouds because there is no moisture, but when the jet stream breaks through, it can bring some moisture into this dry area, forming cirrus clouds, thin, wispy clouds. An example of how it works. Imagine you are in a car. If you are driving on a straight highway, your speed is fast and smooth, but when you hit a curve or bump, you might speed up or slow down. The jet stream is like that fast car in the sky. Sometimes it moves smoothly, and other times, especially when seasons change, it might change speed or direction. Additional information. Jet streams don't stay in the same place all the time. They shift around the Earth, and their speed can change depending on the time of day or the season. Jet streams are important for weather patterns. They can affect storms, temperature, and even the flights of airplanes, helping them move faster or slower. In summary, jet streams are super fast winds high in the sky. They change speed with seasons and locations. They can sometimes bring moisture into areas where clouds don't usually form. 2 main types are polar front jet, near the poles, and subtropical jet, closer to the equator. Let me know if you'd like to dive deeper into any part of this. All right, let's break it all down step by step in the simplest way so you can understand everything like a story. Wind speeds and jet streams. The jet stream is like a fast-moving river of air high up in the sky, but its speed doesn't stay the same everywhere. Imagine a long road. Sometimes you can drive really fast on some parts, and other times you slow down. The jet stream is similar. In winter, the fastest part of the jet stream is found near Asia's east coast. This is because there's a huge difference in temperature between the cold land and the warmer ocean. Over places like the Atlantic Ocean and the Pacific Ocean, the jet stream slows down because the temperature difference isn't as big. But when summer comes, everything changes. Now, the fastest jet streams are near the Canadian border and above the Mediterranean Sea. Jet streams in the southern hemisphere. In the southern half of the world, jet streams also exist, but they behave a bit differently. Why? Because there aren't as many large land masses near the South Pole. This makes the jet streams in the south more smooth and symmetrical compared to those in the northern hemisphere. How jet streams move. Jet streams generally flow in a straight line from west to east, but sometimes they bend and meander, wiggle. Imagine a river that doesn't flow straight, it twists and turns. The jet stream does the same thing. These big bends in the jet stream can stretch from the North Pole all the way to the tropics, warm areas closer to the equator. These bends are so big that their average length is 6,400 kilometers, longer than many countries combined. Only about 7 such bends can fit around the entire Earth. Warm and cold air pools. When these bends become very large, something cool happens. Warm air from the tropics can get pushed up to colder places near the poles, and cold air from the poles can get pushed down to warmer places near the equator. Imagine scooping up water from a hot pool and dropping it into a cold pool. That's how the air moves around with the help of jet streams. Sometimes, these pools of warm air get completely cut off from the main jet stream and become stuck in colder areas, and vice versa. Similarly, cold air pools can get stuck in warmer areas. This can lead to cold cyclones, big spirals of cold air, or warm anticyclones, big spirals of warm air. Why does this happen? The jet stream helps maintain a balance between hot and cold air on Earth. This is like nature's way of making sure that heat doesn't stay in one place too long. This back and forth movement of air is necessary to balance the temperatures across different parts of the Earth. Topsy-turvy weather. According to a scientist named Trewartha, when the jet stream gets all wavy and agitated, it causes topsy-turvy weather on Earth. You might have warm weather one day and then cold weather the next. This crazy weather happens because the jet stream is pushing warm air and cold air to places they don't usually belong. Example, let's say you live in a place that's normally warm, but suddenly you get hit with a cold breeze. This could be because a bend in the jet stream brought cold air down from the poles, cutting it off from its normal path. Similarly, people living near the poles might suddenly feel warmer if warm air from the tropics gets pulled up by a large bend in the jet stream. Summary. Jet streams are fast-moving winds in the sky. Their speed changes based on the time of year and the place on Earth. They bend and twist, which helps move warm and cold air to balance temperatures. Sometimes pools of warm or cold air get stuck in unusual places, causing changes in the weather. These changes help balance the Earth's heat and prevent extreme differences in temperature. This constant movement of air from higher latitudes, closer to the poles, to lower latitudes, closer to the equator, helps keep Earth's climate in check and affects the weather patterns we experience every day. Let me know if you'd like to dive into any part of this in more detail. All right, let's break it down step by step using the simplest words and explanations. We'll go over each point carefully so you understand everything. Ready? Let's start. What is a jet stream? Imagine a river of air that moves very fast high up in the sky. This river of air is called a jet stream. It moves from west to east, and it controls how weather moves around the world, the polar region and the mid-latitudes. In this first stage of the index cycle of jet streams, the jet stream is close to the polar regions. What's the polar region? It's the area near the North Pole. So think of the jet stream as being far up north. North of the jet stream, it's very cold because it's closer to the North Pole. South of the jet stream, it's warmer, but not hot. This is the area we call the mid-latitudes. It's where many countries are located, like the United States, parts of Europe, and China. The jet stream's flow. In this stage, the jet stream is flowing straight from west to east. It's not bending much, so it's like a straight highway in the sky. High zonal index. What does this mean? This first stage is called the high zonal index. Don't worry about the complicated words. Let's break it down. Zonal means that the wind is moving in a straight line from west to east without big bends or loops. High zonal index means that the jet stream is very straight, staying close to the North Pole. What's happening in the air? 1. Cold air stays in the north, above the jet stream. 2. Mild, warmer air stays in the south, below the jet stream. 3. There's not much mixing of cold and warm air, so temperate and tropical regions don't share much air. Pressure systems. Now, pressure systems are like invisible pushes and pulls that affect how air moves. In this stage, these pressure systems are lined up east to west, just like the jet stream. The pressure difference between north and south is stronger because the jet stream is straight. Minimal air exchange. Because the jet stream is straight and not bending, there's not much air exchange between the cold north and the warmer south. It's like both sides are staying in their own lanes. Example to simplify. Imagine 2 big rooms, one with cold air and one with warm air, and there's a door in between them. In this first stage, the door is almost closed, so the cold and warm air don't mix much. Each room stays with its own air. Key takeaway. This first stage shows the jet stream staying straight and strong, mostly keeping cold and warm air separate. Because of this, the air doesn't mix much between the north, cold, and south, warmer, which means less movement of weather systems between these areas. Extra info. Later on, in the other stages of the jet stream cycle, the jet stream might start to bend and loop. When it does, the cold air from the north can move south, and the warm air from the south can move north. This would cause more weather changes, like cold fronts and heat waves. But in this stage, things are more stable and calm. Does this make sense so far? All right, let's break down these stages in simple words, step by step. What is happening in the second stage? In this second stage, the jet stream, the fast-moving air high up in the sky, starts to bend and wave. Imagine the jet stream as a wiggly line now, instead of a straight one. 1. The whole jet stream moves south, closer to the equator. The equator is the middle part of the Earth, where it's usually warmer. 2. Cold air from the polar region north starts to move south. This means cold air is traveling down towards warmer areas. 3. Warm air from the south, from the mid-latitudes, moves north. Now, the warmer air is pushing up towards the colder areas. So in this second stage, the cold and warm air start to mix more as the jet stream bends and moves. Example to simplify. Imagine a door between the cold room and the warm room, just like in the previous stage. In this second stage, the door starts to open wider, so cold air enters the warm room and warm air enters the cold room. What happens in the third stage? In this stage, the jet stream's waves become even bigger. The jet stream is now really wiggly, and this causes 1. Warm air masses move farther north. 2. Cold air masses move farther south. The jet stream is now closer to the equator, meaning the cold and warm air are mixing even more. Temperature gradient changes. Now, something else happens. The temperature gradient, difference in temperature, changes. It now runs east to west instead of north to south. This means that as the jet stream bends, you have warm and cold air spread horizontally more than vertically. Example to simplify. Imagine the cold room and warm room again, but now the door is wide open. The cold air moves far into the warm room, and the warm air moves far into the cold room. There's a lot more mixing of air between these two regions. What happens in the last stage? In this stage, the jet stream has giant bends, called meanders. These bends are so big that parts of the jet stream break off from the main stream. Here's what happens. 1. A large pool of cold polar air gets stuck in the lower latitudes, warmer areas, far from the poles. This cold air is now surrounded by warmer air masses. 2. In the higher latitudes, closer to the poles, some warm air from the south gets trapped by cold air. This stage is called the low zonal index because the jet stream is no longer straight and west to east like in the first stage. Instead, the jet stream breaks up into smaller parts called cells. Example to simplify. Imagine the cold and warm rooms again. Now imagine that instead of one big door, there are small doors all over. The cold air from the polar region moves into the warm room and gets stuck there. Meanwhile, warm air moves up and gets trapped in the cold room. Key takeaway from all stages. First stage, jet stream is straight, cold and warm air stay mostly separate. Second stage, jet stream bends a little some, cold and warm air start mixing. Third stage, jet stream bends a lot more, with much more mixing of cold and warm air. Last stage, the jet stream breaks into smaller parts, and cold air gets trapped in warm regions, while warm air gets trapped in cold regions. In this last stage, the jet stream becomes weaker and more fragmented. This stage leads to big weather changes, like very cold areas in warm places or very warm areas in cold places. I hope this makes sense. Let me know if anything needs more explanation. Let's break this down step by step to make it super simple. What is a jet stream? A jet stream is like a fast-moving river of air high up in the sky. It's very strong and moves from west to east around the Earth. These jet streams are very important because they affect our weather on the ground. Relationship between jet stream and weather. Even though scientists are still trying to fully understand the jet streams, they know that jet streams are closely linked to weather changes. Here's how. Jet streams help to move weather systems, like rain, snow, or storms, from one place to another. They control where cold air and warm air will go. When the jet stream bends or changes, it moves cold air from the poles to warmer places or pushes warm air toward colder regions. When the jet stream bends in a certain way, it can bring rain, snow, or even dry conditions. Polar front jet stream. There's one specific jet stream called the polar front jet stream, and it's very important for the weather in the middle latitudes, places like the United States, Europe, and parts of Asia. It helps to create and control storms and cyclones. These are strong weather systems that bring rain, wind, and snow. The jet stream affects where these storms will go. The polar front. This is the line that separates cold air from warm air on Earth. The jet stream helps control this line. Influence on precipitation. Jet streams also affect how much rain or snow a place gets. If an area is directly under the jet stream, it's more likely to get heavy rain or snow. This is because the jet stream helps move moist air to these places, which leads to precipitation. How jet streams affect different weather patterns. 1. Droughts or floods. If the jet stream stays in one place for a long time, it can cause droughts, very dry periods, or floods, too much rain, because it keeps the same weather pattern in one place. 2. Cyclones. The paths of cyclones, big rotating storm systems, are largely influenced by jet streams. The jet stream acts like a road for these storms. 3. High and low pressure systems. High pressure usually brings clear weather, and low pressure brings stormy weather. The movement of these high and low pressure systems is also controlled by the jet stream. Example to simplify. Imagine the jet stream as a racetrack in the sky. Weather systems, like storms, rain, or clear skies, are the cars on the track. If the racetrack bends or changes direction, the car's weather will follow it. The jet stream decides where these weather systems will go. Importance of understanding jet streams. The better scientists understand jet streams, the better they can predict the weather. For example, they can know if a place will get a cold wave, sudden cold weather, rain, or even a tornado based on the position of the jet stream. Key takeaway. Jet streams are super important in controlling weather all around the world. They help decide where storms go, how much rain or snow a place will get, and even if a place will have droughts or floods. Scientists are still learning about jet streams, but they already know that these powerful air currents have a huge impact on our day-to-day weather. I hope this simplifies the concept. Let me know if you need further clarification.